Hello, my name is Noah Ash, and I'm a junior at the University of Washington, majoring in atmospheric sciences and minoring in applied mathematics. I work with Dr. Anderson-Frey, an assistant professor in the atmospheric sciences department, on exploring tornadic environments in the United States. This project started in the fall of this academic year, so we have been researching for more than half a year together. My research topic explores how a plethora of tornadic parameters are altered by examining specific geographic regions of the United States. Furthermore, we look at how the seasonality in these respective geographic regions affects these parameters by comparing and contrasting similar seasons in different geographic regions for certain environmental parameters. The hypothesis formed through our work is as follows. Changing geographic and topographic features, along with seasons, will heavily impact the trends examined in tornadic activity. For this coding-heavy project, I relied on using Jupyter Notebook. We wanted lots of statistics, so I downloaded sklearn to run statistical analysis such as kernel density estimations and quantile-quantile plots. Coding via sklearn allowed me to visually represent statistics, allowing for a clear picture of trends that would be tough to see if solely looking at the raw numbers. Additionally, I used filled contour maps to see trends plotted across the whole United States for given years. There is a fair bit of interpolation, but it allows us to see the flow of various parameters throughout the years. The dataset we used is the NOAA Storm Prediction Center dataset, which measures a multitude of tornadic environmental parameters spanning from 2003 to 2017 all across the United States. This Excel file was simply converted to a CSV file and downloaded using pandas in order to begin extracting the data on Jupyter Notebook. Our first set of plots shows contour plots created across the entire United States. We can see areas with higher magnitude tornadoes, changes throughout the 4 years I selected. These were some of the more exciting years to choose from. Using the linear interpolation creates a heat map that clearly shows where the strongest tornadoes are, red being where the more intense tornadoes on the Fujita scale are, and dark blue being where the tornadoes that are the least intense on the Fujita scale are. Looking at these plots, we can clearly see that in 2008, in the top right corner, the strongest tornadoes seem to hit Iowa down to Missouri and Arkansas. However, if we look at 2011 in the bottom left corner, we can see the shift of intense tornadoes moves to the southeastern region of the United States. This year-to-year variability goes to show the wide range of the United States that experiences tornadic activity. The second set of plots shows a measure called CAPE, convective available potential energy, which is like the amount of fuel a storm has to develop. The more CAPE in the system, typically more intense the storm is, as it has more energy to develop into severe weather. We have 4 plots of CAPE over the summer, and as we can clearly see, the regions of the United States that experience more tornadoes overall, on average have a lot more CAPE, or potential energy, as they need this CAPE to form massive supercells that we commonly see in places like the Midwest or Tornado Alley. The overall goal for this research is to create a more nuanced tornado climatology in order to better understand tornadic behavior across the United States. In doing so, we hope to make preparation for tornadoes safer so less people are harmed when they hit. So far, we've discovered many noticeable variations in the environmental parameters for given regions of the United States, some of which were discussed in the past slides. Our next goal is to look at how topography, such as mountains, deserts, and major bodies of water affect these parameters. Thank you for listening, and I hope you enjoyed.